Hello and welcome to this video. This is a tutorial for the plugin UnderPCB for KiCad, a PCB design tool. Let's get started. To use UnderPCB, you'll have to use PCB new in KiCad, and once you have a project loaded up, you can start up UnderPCB by clicking on this button at the top. But to get to this point, you first of all have to install UnderPCB. There are multiple ways to do this. Here's some install variants. First of all, you could just casually insert a plugin like any other plugin by moving the plugin files, the Python files, including the plugin folder, to one of KiCad's paths where plugins are stored and looked up, and install the Python requirements by hand, which are located in the pip requirements.txt file. Two other ways would be to install the .deb file and the .rpm file, which would include the dependencies inside the file. Once you've done this, you can start to use the plugin. This plugin is not just a plugin itself, it also has a server counterpart where machine learning calculations are done, and as well as a model and training set collection. So you also have to kind of install a server and deploy it. Some variants are to run the server manually and install the requirements. As well, it's a Python server, so you have to install requirements dependencies via pip or your Python package manager of choice. You can also install a .vhal file with pip, or you could install and set up Docker, and if you intend to use the plugin only locally with a server running in the background. That way the plugin will then download and deploy the server in the background on itself. This is the setup I'm using right now. Now let's cover the settings. When you start up the settings, you'll have some options of different kinds. The interesting one, first of all, is the server type setting. You can choose to use a remote server, so you have to then give the plugin a server IP address as well as a port, or you can choose to let the plugin start a server on its own in the background via Docker. As well, give it the option to use either the CPU or the GPU if a compatible GPU is accessible. Also, you can choose to save filter data locally, so an analysis usually takes some time, it's roughly between 2 and 10 minutes, depending on the board size. So by choosing to save the files, you can reopen the results later on with just a small delay. Also, this plugin is currently configured to provide 8 different signal types, and instead of the signals having numbers, you can give the signals names to differentiate between them more easily. This is the standard given and also the standard used by our trained model, though you can choose to change the signals, but keep in mind that you'll have to keep this consistent throughout your model training and usage. You'll also have to change the slice size at some point. The X size can stay the same, 28 is a roughly good number, and the Y size must be configured to match the size of the number of the layers of the board. So in this case we have 4 metal layers, front, inner 3, inner 2 and back, that's 4, so we have to use a slice size of 4. Those two numbers also have to match model sizes, and you have to keep it consistent, this also being a standard. When you use the plugin and analyze a new board, let's say you have a pre-trained model which matches the sizes and configuration of this board, then there's still a step missing before you can do your analysis. You have to provide annotations for your board, the signal data, and those are annotated to each net. So we can take a look at this board. This is the Jawbreaker board, and this is already a fully annotated board. And we can just choose some wires. At the bottom you see this has a net code and a net name, and this will then have an annotation to it. So we can take a look at it with the pencil button, and we see that it has the signal digitized table. We can also take a look at multiple ones at the same time, and we see that all of those nets have the digitized table annotation. At some other point we'll probably see some other annotations. Yep, here we have an analog sensitive signal. But this would be tedious to do this by hand, dependencies. So instead of that, we provide a util for more easier and automatic annotation. So if you open this regex tool up, and you can annotate your whole board with naming patterns. So let's say you design your schematics and give the nets names. Then you can append, let's say, a digstable to your names at the end, and then automatically give it the annotation digitstable. You can continue the list with those naming patterns, and at the end annotate the whole board. You can also take a look at the net list with this button here, and also choose to annotate the signets right here with a double click. When this whole board is annotated, you can start analysis, and you can find it out by either taking a look at this net list. If the list on the right side is empty, then all nets are annotated. Or you can also click on this light bulb button, because the light bulb will highlight any net not annotated yet, so you can take a look at it in a location and neighborhood for the last few nets which maybe have no name or etc. Once you've annotated your board, you could start the analysis, but first of all you will have to choose a model. So we also have to take a look at the server options with this button here. So now the plugin will start the server in the background, and now it's running. And it will give us a list of the models it has, and we can just choose one of those and serve it, and then it's chosen for us. And now we could start the analysis. So let's say we have already a pre-trained model fitting the options. That would be the scenario for your design process. And now you could start analysis, but because this is taking some time, I'll skip this and instead just show the results. So this will load up the files in the background. And now it's finished, and we're given two windows, one being the PCB layout, where you can scroll through the layers, and one being a histogram of the board analysis. When analyzing the board, the algorithm will take a look at each position in the board where a net is running through, and create a slice and analyze the slice. And by doing that, it can detect anomalies from the standard design patterns, and such deviations will result in a high reconstruction error. Because the algorithm should be able to recognize most of the board, we obviously have a huge amount of slices and checks where the result resulted in a small error, and the interesting ones are the ones which result in a high error, which have a low amount of. To take a look at those interesting slices with a high error, we can now use the right window and choose a threshold. And choosing a threshold will mean that after clicking on view, every slice with an error higher than this given amount will then be rendered on the board, and each slice with an error which is less than this will be ignored. So let's take an error of 0.013 and click on view. So now it's rendering some slices. This is also done in different colors because we cluster on the compressed slices, the latent representations, so we can potentially detect different error types. So you can see some of them are grouped together with the same color, but we can also choose to decrease the amount of different colors. And if we're not satisfied with the result because we have too much drawn on it, we can also decrease the amount of drawings even further. Once you've done this, the designer should try out different values and try to find out some interesting spots which may have potential anomalies. This is a board which is already a working board, which is also present in the training data, so we don't have a use case to show here. But let's say here's a wire which is marked with a high error. That would be reason enough in a normal design process to just go ahead and take a look at it again and try to find out whether there is a potential anomaly or not. And doing this should let you find some anomalies which you've missed out in the design process. Also, you can choose out to use different clustering algorithms, but k-means is the one you should be using because this gives you the most amount of control. Also, because we change some data in the plugin, as for example, the annotations, as well as the saved results, as well as the settings data, we save some data, and this is done in the project folder. So this is the folder where Jawbreaker is contained, and our plugin files are saved in JSON files, if you want to take a look at them. And you could, for example, copy the regex files into new projects to have this same naming scheme list to automatically annotate the board. The settings are also saved here as preferences. And if you want to really save the preferences, you'll also have to save the board after changing the settings, because this is the time where the settings are saved. So yeah, now let's get to the model creation and training. Up to this point, I've talked about having pre-trained models, but this is not always the case. For example, if you need a new model, or if you want to increase the accuracy of your models, then you'll have to start fresh with a new model. A model is first of all an abstract file having the specifications for the model without any data. Those are not limited to any structure, just the inputs and outputs have some requirements. And we offer a sample autoencoder which you can use, but also extend as you want. And running such a file will generate a template file, which can then be trained to a model which can then accomplish the analysis process, like this file here. Please also consider that a template file will also have fixed slice size. So yeah, when we want to start with that, we first of all have to send a model. Like this, and then serve it. Once done, we can then use this train window here and start the training process. But prior to starting the training process, you'll want to have some data sets for the training process. In this case, I only have the Jawbreaker data in. This is a bug I still have to fix. And then you can select multiple files and start the training process. Also, this A at the end means that it's an augmented dataset. You can see the button right here on the bottom. And importing new datasets is done by using the Send Slices button. Instead of that, you can also import slices, which can be exported from the settings. And those datasets are saved on the server. You have options for the batch size, the maximum training time, and the maximum training parse. And you can try out different numbers until you're satisfied with your training results. Training your models is a heavy computational process, so it's good if you use a proper graphics card for this process. Once the training process finished, you'll be greeted with a window showing the results, performance of the model, then this model, in this case autoencoder template X28Y4, which is located on a server, will then be fully trained and will then give reasonable results and analysis process. Thanks for listening to this tutorial, and I hope that you'll figure out to use this plugin and that you'll have some great results with it.